Now let's talk a little bit about the wave function for the particle enclosed in a box. That wave function is a times the sine of n pi over L times x. This actually comes from this wave function right here. E to the I kx can be written as cosine kx plus I sine kx. Then if we combine a right-moving e to the I kx with a plus and a left-moving e to the I kx with a minus, we can get this cosine term to cancel out. Standing waves are always a wave moving left and a wave moving right. And we're left just with this sine kx term. And then the fact that the particular values were sine of n pi x over L are simply the restrictions we need so that when x equals 0 or x equals L, the wave function will be 0. Now remember the meaning of a wave function. The meaning is that we get a probability distribution by squaring it. In other words, the probability of finding the particle between a point x and a point x plus dx, just a little bit further away, is equal to the wave function squared times dx. The bigger dx, clearly the bigger the probability. But for a given size dx, the probability depends on how big that wave function is. So if we use this wave function here and bring this up, we find that the probability distribution is a squared sine squared of n pi over L times x. Now let's look at that for a few values of n. One key thing to remember is that because we are in an infinite potential well, we cannot have any probability of finding the particle exactly at the walls, because that's infinite potential, and the particle can't be there. So we're not going to find the particle at the walls. And in fact, when we look at the very first state, the ground state, the particle's probability of being even anywhere near the walls is quite small. Notice we do have 0 probability exactly at the walls, and there's only a large probability of finding the particle right in the middle. If I change to n equals 2, we see something even more surprising. There's a place right in the dead center where we'll never find the particle at all. However, there is a probability of finding it near the center of the left half and the center of the right half. For n equals 3, we have 3 bumps. Notice these are not much like we would expect classically. Classically, we would expect to have an even distribution everywhere throughout. Find the same probability of finding the particle anywhere within the box. Well, let's look at the case for n equals 15. Notice that for n equals 15, we have 15 different bumps, all of essentially the same height, and they're very close together. So, if my dx's aren't too small, in other words, if they're bigger than the distance between these bumps, we are going to find an even probability all the way across. Now, it is true that for n equals 15, there are still places that if we measure carefully enough, we can't find the particle. But imagine that n went from 15 to, say, 200. Pretty soon, the size of these bumps is much smaller than the size of any measuring device we could use. And it starts to appear that we have a completely even probability distribution. Same probability of being found anywhere within the box. And that is our first example of a general principle of quantum mechanics, which is that as the quantum numbers, as the state we're in, get large, then the quantum physics prediction needs to merge smoothly with the classical physics prediction. In other words, at large quantum numbers, which is the world we live in from day to day, the quantum theory better give the same results as our classical theory, because we know the classical theory works great in our daily world. Let's come back and talk a little bit about this coefficient a. It's not, in general, just a random number. We have to pick it according to the meaning that the wave function squared is a probability distribution. And the key idea is that the probability of finding the particle somewhere inside that box has to be 1. In other words, if I were to integrate p of x dx from 0 to 1, or from 0 to L, that had better equal 1. A probability of finding the particle somewhere exactly equal to 1. Well, if we take that condition, then we just say, in our case, in general it's an integral from negative infinity to infinity, but in our case, the particle only exists between 0 and L. So the integral from 0 to L of a squared sine squared of n pi x over L dx had better equal 1. It turns out that if you integrate sine squared over at least half a cycle, or any integer number of half cycles, which we always do here, it averages to 1/2. So this left-hand side is always going to end up being a squared over 2 times L. And that has to equal 1, which tells us that a is going to be the square root of 2 over L. In general, we can have a complex phase on it, but we really don't need it, so why complicate?